In this video, we will introduce what quadratic residues modulo n are, and give the simplest brute force methods for determining which numbers are or are not quadratic residues. First up, of course, we have to introduce the definition. Let n be a positive integer and a be any integer. If there is a solution to x squared is equivalent to a modulo n, then we will say that a is a quadratic residue modulo n. Quadratic residue, simply meaning residue, it's one of the residue classes mod n, and it's quadratic, it is the square of something else. There was an x, so that x squared was equivalent to a. However, if there is no solution to the above, in other words, no matter what integer x you pick, x squared is never equivalent to a mod n, then we'll say that a is a quadratic non-residue mod n. Depending on the source where you get this definition, 0 may or may not be considered a quadratic residue. The way I've worded the definition above, 0 is definitely a quadratic residue mod n for any n, because there is an integer x, specifically 0 itself, so that x squared is equivalent to 0 mod n. 0 squared is always going to be equivalent to 0 mod n, no matter what n is. Other sources may specify that a equals 0 is simply not allowed if you're trying to determine quadratic residues mod n. The only thing that really changes is, when we phrase certain theorems, we may specifically say non-zero quadratic residues to rule out the case of a 0. Other books that throw that out at the beginning can just say quadratic residues because they've already gotten rid of 0. It's not generally the biggest issue. Now let's take a look at some examples. I claim the following three things. 9 is a quadratic residue mod n, no matter what n you pick. 5 is a quadratic residue mod 11, but 5 is not a quadratic residue. In other words, it's a quadratic non-residue, modulo 7. Well, first up, why is 9 a quadratic residue mod n? Because 3 squared is equal to 9 as an integer, 3 squared will be equivalent to 9 no matter which n we pick. So there was a solution to x squared equivalent to 9 mod n. Just let x equal 3, or negative 3 for that matter. Therefore, 9 is a quadratic residue mod n. So at this point, students may think, how can 5 be a quadratic residue mod 11? There is no integer whose square is equal to 5. That's true, but 4 squared is 16, and 16 is equivalent to 5 modulo 11. So there is an integer whose square, while not equal to 5, is equivalent to 5 modulo 11. Therefore, 5 is a quadratic residue modulo 11. But modulo 7, if I pick any integer, it's got to be equivalent to something from the standard complete residue system mod 7. Either x is equivalent to 0, or 1, or 2, or 3, or 4, or 5, or 6. Now if I square all of those possibilities, 0 squared would be 0, 1 squared is 1, 2 squared is equivalent to 4. Now 3 squared is 9, but 9 is equivalent to 2 modulo 7. 4 squared is 16, which is equivalent to 2 mod 7. 5 squared is equivalent to 4 mod 7, and 6 squared is equivalent to 1 modulo 7. So no matter what x is, it's equivalent to something 0 through 6. Therefore, its square is either equivalent to 0, 1, 4, 2, 2, 4, or 1. Nothing in a complete residue system mod 7 squares to be equivalent to 5. So there is no integer whose square is equivalent to 5 modulo 7. So 5 is a quadratic non-residue mod 7. The important thing to pick out here is that 5 is a quadratic residue mod 11, but is a quadratic non-residue mod 7. So the base really matters. You can't just say something like 8 is a quadratic residue. You would say something like 8 is a quadratic residue modulo 25, or something like that, which probably isn't true. But in any case, it has to be an integer is a quadratic residue modulo a base. That last bit is crucial for the definition. With the definition under our belts, let's work through an example. Determine which integers are quadratic residues modulo 14 and which are not. We're just going to do the brute force technique we introduced on the last slide. We're going to take the entire standard complete residue mod 14 and square things. So 0 squared is equivalent to 0, 1 squared to 1, 2 squared to 4, 3 squared to 9. 4 squared modulo 14 is equivalent to 2. 5 squared is equivalent to 11, 6 squared is equivalent to 8 mod 14, and 7 squared is actually equivalent to 7. This might look a little surprising, but if you check, 7 squared is 49, and 49 is 3 times 14 plus 7. So it is equivalent to 7 modulo 14. 8 squared is actually equivalent to 8, 9 squared to 11, 10 squared to 2, 11 squared to 9, 12 squared to 4, and 13 squared to 1. So now what we've done, we've taken the entire complete residue system mod 14, the standard one. So we've taken the numbers 0 through 13 and squared them all, and then asked which element of the standard complete residue system, mod 14, are they equivalent to. The only integers we got out by squaring things were 0, 1, 4, 9, 2, 11, 8, and 7. So those are quadratic residues mod 14. Anything we didn't get out from any of our possible squares are quadratic non-residues mod 14. So 3, 5, 6, 10, 12, and 13 were never produced by squaring anything in the complete residue system mod 14. Therefore, those are the quadratic non-residues mod 14. One thing to look at is that if you are looking in the real numbers, x squared equals x, there's only two numbers, 0 and 1, that when you square them equals itself. But modulo 14, x squared equivalent to x mod 14, had 4 different solutions. 0 squared was equivalent to 0, 1 squared to 1, 7 squared to 7, and 8 squared to 8. So there were 4 different residue classes that solve x squared equivalent to x mod 14, even though in the real numbers, x squared equals to x would boil down to finding roots of a degree 2 polynomial, and there can be only 2. So modular arithmetic will work fundamentally different than real or complex valued arithmetic when we are working with polynomials. Let's continue with some observations along those lines. So polynomial equations in the real or complex numbers are just going to be different from polynomial equivalences modulo n. The equivalence, x squared equivalent to x mod 14, had 4 solutions. So if I subtract x from both sides, x squared minus x equivalent to 0 had 4 solutions. So we can say the polynomial x squared minus x has 4 different roots modulo 14. So even though it's a degree 2 polynomial, there were 4 distinct roots as long as we're working modulo 14. So we're going to continue to investigate differences and possible similarities between how polynomials behave in the real or complex numbers and how they behave modulo n. For now, you may have noticed something else every time we've done this brute force computation. When we computed which numbers are or are not quadratic residues, we did it modulo 14 on the previous slide, and we did it modulo 7 a few slides back. There was a certain symmetry as you compute x squared. Basically, since x squared is the same thing as negative x squared as integers, and therefore they will be equivalent mod n, we end up with a nice symmetric arrangement of the quadratic residues mod n. So once you've brute forced your way through the first half of the complete residue system mod n, the second half will only duplicate what you've already seen. So mod 13, for example, 1 squared, 2 squared, 3 squared, are equivalent to negative 1 squared, negative 2 squared, and negative 3 squared. But negative 1 is equivalent to 13 minus 1, mod 13, and negative 2 is equivalent to 13 minus 2, modulo 13. And negative 3 is equivalent to 13 minus 3, modulo 13. So negative 1, as long as we're working mod 13 in all these examples, negative 1 is the same thing as 12. Negative 2 is the same thing as positive 11, and negative 3 is equivalent to positive 10. So since x squared is the same as negative x squared, we get this symmetry. 1 squared matches up to 12 squared, 2 squared to 11 squared, 3 squared to 10 squared, and so forth. 4 squared to 9 squared, 5 squared to 8 squared, etc. So whatever quadratic residues are built up by going up the first half of the standard complete residue system will then be mirrored as you count down the top half. While we have seen that polynomials can do unexpected things modulo n, if we're working in a prime base, things are a little easier to get a handle on and a little more familiar. So the quadratic equivalence, x squared equivalent to a modulo p, where p is an odd prime and a is relatively prime to p, either has no solutions or exactly 2 solutions. This lines up a little bit better with how we expect polynomials to behave. Notice that modulo 14 we were able to find more than 2 solutions to certain polynomials of degree 2. Here, however, we're saying that the specific quadratic equivalence x squared equivalent to a, which is relatively prime, to the base p, which is a prime number and is odd, either there's no solutions, either a is a quadratic non-residue, or there's exactly 2, which is kind of what we would expect for a degree 2 polynomial. So suppose that there are any solutions at all. So maybe there's 0 solutions, but let's suppose there's at least 1. So I found a certain x so that x squared is equivalent to a mod p. Well, then negative x squared is also going to be equivalent to a modulo p. If x is the same value as negative x, however, this isn't actually a new solution. But since a and p are relatively prime, a is not equivalent to 0 modulo p. So therefore, if we assume x is equivalent to negative x mod p, then 2x is equivalent to 0 mod p. In other words, p is a factor of 2 times x. P was odd, so it's relatively prime to 2, and therefore it must be a factor of x, and therefore x must be equivalent to 0 modulo p. But if x were equivalent to 0 mod p, so would x squared be. But x squared is equivalent to a, and p isn't a factor of a, so I can't have it both ways. So what we conclude is that if there are any solutions to x squared equivalent to a mod p, where p is an odd prime and a isn't equivalent to 0, then if there's one solution x, there's another solution negative x, and those are in fact different solutions. So if there are any solutions, there are at least 2. So having established that whenever there are any solutions, there are at least 2 solutions, what we need to do next is show that there can't be any more, because the claim of this theorem is that if there aren't 0 solutions, there are exactly 2. We now know if there are not 0, there are at least 2. We just need to show these are the only ones. Since x squared was assumed to be equivalent to a modulo p, then p is a factor of x squared minus a. This just comes from the definition of modular equivalence. Okay, so where are we and where are we trying to get? If a is relatively prime to p, and x squared is equivalent to a mod p, what we need to do is show that if we find another solution y, the only possible other solution to find would be x or negative x. So whenever there's a solution, there's at least 2, but if we can establish this, then having found one solution x, the only other solutions would be x and negative x, so there are only 2 solutions. Suppose we have this, so x squared is in fact equivalent to a, but so is y squared modulo p. Then x squared must be equivalent to y squared mod p, so p is a factor of the difference. But that difference, x squared minus y squared, factors very easily as x minus y times x plus y. So now we have a prime number that's a factor of these 2 things multiplied together, the 2 parenthetical terms. So a prime number is a factor of one number times another, which means either it's a factor of the first, in which case x is equivalent to y mod p, or perhaps it was a factor of the second, in which case x is equivalent to negative y mod p. Either way, y is either equivalent to x or y is equivalent to negative x. So once we assume x is one solution and y is another, they must be equivalent to plus or minus each other. So if there are any solutions, there are at least 2. What we've shown here is that there are at most 2 solutions. Therefore, there are exactly 2 solutions whenever there are any solutions at all. So if A is a quadratic residue mod P, where P is an odd prime, so if it is a quadratic residue, there are some solutions to x squared equivalent to A mod P. What we've just shown is the only other solution is exactly given by negative x. We get a really nice immediate corollary from that previous observation. Suppose P is an odd prime. In any complete residue system mod P, there are exactly P minus 1 over 2 non-zero quadratic residues and P minus 1 over 2 quadratic non-residues. As a proof, in any complete residue system mod P, there's going to be P elements. One of them is equivalent to 0. Set it aside, because the statement of the theorem specifically says non-zero quadratic residues. So having removed 0 from consideration, there are exactly P minus 1 non-zero elements left. Each of these elements x, we're going to square, and we have to get out something. So I have P minus 1 elements, and I'm squaring them. Since x is not divisible by p because it wasn't equivalent to 0 mod p, x squared is also not divisible by this prime number. So whatever x squared is, it's also not equivalent to 0. Negative x is in the same complete residue system, and it has to be different because p was odd. Remember, when p is an odd number, x and negative x are never equivalent to one another. So x and negative x are two different elements which do square to be the same thing. But nothing else can square to be whatever that was. If x squared is equivalent to a, then so is negative x squared. But nothing else can square to be equivalent to a because the polynomial x squared equivalent to a mod p can have exactly two solutions or 0. So whatever numbers are non-zero quadratic residues have exactly two numbers that square to be equivalent to them. So there's a really nice 2-to-1 relationship being set up. The non-zero elements on the one side and the non-zero quadratic residues on the other. For everything that is a non-zero quadratic residue, there's exactly two things that square to be equivalent to it. So there must be p minus 1 over 2 non-zero quadratic residues. There were p minus 1 elements that I can square, and then I pair them up 2-to-1 to what their resulting squares are. So of the p minus 1 squares, since every 2 of them produces one unique square element, then there are p minus 1 over 2 non-zero quadratic residues. Well, if there were p minus 1 total elements in the complete residue system that are not zero, and half of them are quadratic residues, then the other half must be quadratic non-residues. In other words, working modulo p, once you kind of set aside the element which is equivalent to 0, as long as p is an odd prime, half of what remains in a complete residue system are quadratic residues and half are not. Let's look at an example. Find all of the quadratic residues modulo 23. So we're just going to brute force our way through this, but with a couple small observations that we've already made. 23 is an odd prime. So other than the 0 element, there are 22 elements in a complete residue system. Half of them are quadratic residues and half of them are quadratic non-residues. By brute force, all we have to do is square the first half of the standard complete residue system. 1 squared, 2 squared, 3 squared, 4 squared, all squared to be less than 23, so this is all just going to go quite standard. 5 through 11, I just have to square and then reduce modulo 23 because we are working in the standard complete residue system. And observe, we haven't repeated any values. We couldn't possibly, because once I go past 11, 12 is equivalent to negative 11. So 12 squared will be equivalent to 11 squared. 13 is equivalent to negative 10. So 13 squared will be equivalent to 10 squared. 14 squared, 15 squared, etc. And that gives me the 2-to-1 relationship that I know a prime base has to have, an odd prime base specifically. Therefore, these first 11 values will all be different from one another, and they will be the only 11 quadratic residues modulo 23. So if we were to keep going, we would just duplicate everything. So the quadratic residues mod 23 are just what we have gotten out so far, and placed into order. I have 1, 4, 9, 16, and so forth, and I take this list and I put it into order. So the quadratic residues modulo 23 are 1, 2, 3, 4, 6, 8, 9, 12, 13, 16, 18. Everything else is therefore quadratic non-residues. Notice what we haven't been doing, however, is we haven't been using a square root sign. Okay, we're just talking about x squared equivalent to a modulo m, but we're not taking a square root here because we don't want to confuse the issue. X squared equivalent to 13 modulo 23 definitely has a solution. 6 squared is equivalent to 13 mod 23. But as a real number, the square root of 13 isn't even an integer, and we don't want to introduce that kind of confusion. Okay, so we are avoiding using any square root signs or fractional exponents.